recording.
Great.
Well, welcome to the July 16th, 2024 session of TAPR and HamSCI technical session. My name is Dave, KB0S. And this week, I've been trying to work on, now that I got my RX 888 working properly again, trying to explore more parts of K9Q radio than just collecting whisper and grape type data. So I have been setting up other small computers connected to small radios and trying to work with them, and some have been successful. I've still got a couple that I haven't quite figured out. Maybe if I have time, I'll ask Phil. Anyway, that's it for me. Next on the list is Nathaniel, W2NAF. Go ahead, Nathaniel.
Thank you very much, Dave. This week I've primarily been working on the large-scale traveling ionospheric disturbance project that I'm working on with Bill Engelke and that team, and we're making some progress with the automatic detection and measurement of these things. It still is tricky, still has a lot of work to go, but that's really where I've been putting the majority of my time so far. So in addition to the new baby and the family. That's pretty much been it. Back to net.
Very good. Next on the list is Dave, KD0EAG. Go ahead, Dave.
Oh, hello. Not a lot to report. Just keeping track of everything, answering an occasional question. Somebody has a problem with a magnetometer. That's it from me. Back to you all.
Okay. And next on the list is Phil, K9Q. Go ahead, Phil.
Hey guys, as I was saying for the pre-meeting here, I've been still continuing to experiment with looking at the feasibility anyway of doing the software reference track using the 5351 to track an external carrier that is injected into the front end rather than a reference port. I think it's doable. It won't be good, of course, as a hardware reference, but it's an alternative for those who don't want to modify their 888s and make them interoperable without a hardware external reference. That's one. Oh, two, I was reporting erroneously, as it turns out, that I was running the problems with lost reference clock cycles. I believe now that it was the computer I was running it on. I didn't have this problem before, and it went away when I moved to back to another computer, and I don't know why it's happening. There's plenty of cycles on the machine. There must be something funny about either scheduling or the USB subsystem in that particular computer. It's an Intel NUC that I've had for a couple of years. So, yeah, the USB subsystem is kind of to me, a black box on most computers. And we're kind of pushing it at its limit with these devices, and it's gonna be difficult to debug. Anyway, that's it.
Okay. Next on the list is Bill Engelke, AB4EJ. Go ahead, Bill.
Well, not a whole lot to report on the project. Nathaniel has this new baby, and let me show you what I have. Let's see, where is the show screen? Oh, come on. Here, there it is. I think it got the right screen. No, try it again.
Well, you had a screen for a bit, but
Oh, a doggy.
Yeah, this is, she went for her first boat ride this weekend. She enjoyed it very much, as you can see.
Oh, that's adorable.
Mm.
Like a life jacket.
She's a toy fox terrier. She weighs about 5 pounds right now.
yeah.
Wow.
Anyway, this is it. I've just been distracted with that a little bit. So
Well, Franco's got his up too.
I'm a corgi.
oh yeah, I love corgi.
It's a corgi.
Not
Oh
gonna
my
go
God.
to the life
It's a
jacket.
big corgi.
So, Bill, is that it?
Yeah, nothing else to report.
Okay. Next on the list is Bob in 5BRG. Go ahead, Bob.
Well, hello, everybody. I've got a new baby calf, if that counts. I didn't bring it in here to hold it in my arms. Still trying to figure out whether it's a bull or a cow, but anyway, not a lot to talk about. I'm still working on my software a little bit. Got to correct a couple of problems maybe, and then get it published here. But
Very
back
good.
to you, Dave.
Look forward to seeing that and trying it. Next on the list is Dave W6OQ. Go ahead, Dave.
Hi. Yeah, I'm here. I'm here just to learn about what's happening.
Okay, well, good. Next on the list is Dave Julian, WB9YIG. Go ahead, Dave. Oh, I'm not hearing you. Now try unmuting again or something. I don't know. Maybe not. Can anybody hear him? No,
No.
but hopefully you can listen to us. Okay. Next on the list is Dave McGaw in 1HAC. Go ahead, David.
Good evening, everyone. I've ordered one of those less expensive RX-888s, one of the adapters, and a couple of the isolation transformers. This one is intended to go in the lab and see if we can run our AM Doppler on it. Trying to get our stuff steered in the direction of what we're doing here. The other big thing this week was, well, it was last week, but later is Nathaniel and I, Christina and Mike Hardinger had a nice talk about potential new citizen science initiative that I've been asked to help with. I think there's a good chance we'll be able to use the various projects that we've been working on here to support a upcoming spacecraft if it gets selected. And the PI on the spacecraft is my other boss, the one that I did the balloon project with some years ago. And she does really good proposals. So keep our fingers crossed, but I think we have a good chance of getting this one, but it'll be a little while. Propagation today was pretty wonky. I don't know if anyone else noticed, but I was getting very weak signals and they were changing around. I mean, 20 megahertz WWV was popping in and out at random. So the sun keeps us in business, I guess. There's a lot to study. Back to Net.
Very good. Next on the list is Franco K4VZ. Go ahead, Franco.
Hey, thanks, Dave. Good evening, everyone. Not much to report on the side of the DFC, Phil Harmon's project. I think they're still trying to figure out why the DAC doesn't work. However, a lot of progress made with Tom McDermott, and I think we're going to talk about that a lot in a little bit about the new design that he's working on. I think very promising news. And I also been working, as a personal project, figure out the TRX Duo and the FPGA that is in there, and see if I can improve on what Pavel Demin did for the multiple whisper receiver. So I'll report on that once I get some good results. Back to you, Dave.
Okay, very good. Next on the list is Joe K5ATR. Go ahead, Joe.
Hi, good evening. Well, so this is my first time here. I got on the mailing list probably last month sometime, and it's the first time I've been able to join. I just kind of wanted to see what the group is about and get acquainted. And so that's really all I've got. I'm happy to be here.
Very good. Well, we're here talking about SDR radios and using them particularly with Phil's K9Q radio. So a software radio that needs only a minimal bit of hardware to get it off the air and into the computer. So next on the list, we have Joe Last. Go ahead, Joe.
Oh, I just got here. Trying to
Oh,
put.
Joe, W7LUX, right.
Yeah, I need to change that. Let me see if I can rename that to something more useful. But anyway, been trying to get my presentation together for the upcoming HamFest at Flagstaff. And there we go, except I didn't put a space in there. Anyway, having all sorts of fun with PowerPoint and trying to get GIF files to run, and just in general, having a good old time and trying to figure out if the traveling wave that Rob and Gwen put together a very nice poster on is due to actually traveling waves or just the ringing of the Earth's magnetic field from a nearby CME or a CME impact. Anyway, that's what I'm up to.
Well, very good. Next on the list is Majid. Go ahead, Majid.
Hey everyone. Not much to report. Back to you, Dave.
Okay. And I'm gonna skip over Rob again. Sorry, Rob, but I want to make sure I get down to Tom and Scott. Scott usually is mic muted, and he is. Welcome, Scott, N5TNL. And then I want to Tom McDermott, N5EG, and you had comments and maybe something to talk about.
Yeah, it's been a busy week. Had a lot of help from Franco and from Dave Witten. I think we may have found an FPGA that's fast enough to implement a 4-channel receiver and look through the spec. In order to verify that, I installed the Xilinx tools and wrote the barrel log and got it all to work into timeout. So that's good. I prepared some slides, and we may want to cover that when we finish with the roll call. So back to the group.
Okay. And Rob Robinette, AI6 VN. Go ahead, Rob.
Hi. Well, let's see. Most of the last week I spent assembling and shipping the equipment that is to Pierre, VE3 KTB, who's going to take it up to Ellesmere Island later this month and install a Whisper Demon Grape system up there, as well as a Whisper Sonde 8 transmit at a location that is 15 kilometers away. So hopefully within a month or so, we'll have both have at least 7 channels of simultaneous transmit up there, and that 7 bands being 80 meters through 10 meters, skipping only the 12-meter band, which is proved not to be the most useful, the least useful of bands for ionospheric research. So that consumed a lot of time. I had to purchase, assemble, test. I destroyed a 888 in the process of culling one from KFS. So that was consumed most of my week, it seems, on that. In the parallel, I've been doing continuing research with Franco's guidance, in part, on the use of the SDR Play as a receiver. And I think previously I'd reported that it was performing rather poorly. With Franco's help, we adjusted this gain, the LNA and decoding gain, demodulation gain, to the point where it's roughly the same as the other three receivers, the Kiwi, the HF Plus, and the RX888. So all four of them basically perform the same when they're fed the same RF at this point. I don't know why I spent so much time on it, mostly because Phil VK7JJ keeps telling me how marvelous the twice as good an HF Discovery is, twice as good as a Kiwi or a 888. So, and Phil, I so appreciate him that I keep wanting to needle him on the project, but I don't. Anyway, it leads me to, and also I learned some things about the structure of demodulation. Anyway, that's mostly it. Two of the four antennas are down out of KFS as a result of that, because I don't have 888s, but they should be back up. Anyway, I can go on and on and on, but I'll send it back to the net for now.
Okay, well,
Rob, do you have documentation you could share on the SDR play, and which model were you using?
I was using the RP1A and
RSP1A. Okay.
Yeah, RSP1A, and which isn't the most useful for it doesn't have an external clock input, so you can't really GPS stabilize it. And I don't think the clock that they supply is as good as in that RSP1A is not as good as the one that's in the 888. So Phil's software phase lock loop or frequency tracking may not work as well with the 1A.
So I'm gonna land on the moon.
What's that?
Never mind. I didn't have my mic muted. Sorry.
Okay.
Yeah, well, the RSP1A is the lowest end one, of course. We are using RSP Duos and DX, which do have external inputs, and you might try those. I'm certainly interested in what gain settings you've found, because they are rather obscure. Than getting them correct.
Well, it's of course I run them with AGC off so that we can get noise level measurements, and so that makes it more important to establish what the right settings are. LNA equals 3, and then adjust the decoding gain. Typically 30 or 35 seems to work out at KPH, but at KFS rather. But we put high pass plus LNAs ahead of all of our devices. That isn't so important to a device like it has a low noise amplifier, like a HF Discovery doesn't really benefit from it. But you have to have such a filter plus LNA system for a wideband SDR like the 888 or the Kiwi. But anyway.
Okay, well, we'll get back to this, but I want to give Tom a chance to give his slides if he's willing.
Yeah. Let me do a screen share here, and can everyone see the slides?
Yes.
Okay. So I've been looking at a 4-channel receiver, and the issue has been the logic. So this is kind of a block diagram of what I've been looking at. On the left side are 4 RF inputs, and I haven't put amplifiers or filters or anything like that out there. I just am been focusing on the digital part here. So there'd be 4 A to D converters, and we have to somehow figure out how to get those 64 lines into an FX10 chip. And the FX10 has got 32 inputs that can clock at a maximum of about 160, actually just under 160 megahertz. The reference clock at the bottom lower left there comes into is a low jitter clock. It would clock the 4 ADCs, and you need on the order of about a picosecond RMS jitter to keep the dynamic range of the ADCs. And that same clock would clock the FPGA. And then there's a pulse per second that gets conditioned into a digital signal and goes to the FPGA. So I spent a lot of time looking for logic. What the FPGA does here is really pretty simple. I couldn't find discrete logic, a CMOS, that was fast enough. And so the FPGAs were also difficult, but with Franco and Dave's help, we found that the Spartan 7 series from Xilinx looks like it'll meet the timing. We found one part, or Franco found a part. It's about $32 for the FPGA. It's got about 170 I/O pins on it. So I went ahead and installed the Xilinx toolkit, wrote the Verilog, and did place and route and post layout timing analysis. And it does meet the timing requirements. It's able to multiplex the 64 lines into 32. And so the 32 is what's called double data rate. There's a 125 megahertz clock going from the FPGA to the FX10. And on the rising edge of the clock, you clock 32 data bits. And then on the falling edge of the same clock, you clock a different 32 data bits. And so the net throughput there is about 8 gigabits per second into the FX10 chip. So this is the result of the post place and route timing analysis. And you can see on the top the 4 ADC channels, and the 5th line down, you can see the double data rate, which is about 2 clock cycles behind. And then the input clock, and I pinned out 4 output clocks at 90-degree phases. So you can find one that's reasonable to use for the double data rate clock. I've been pretty impressed with the Xilinx part. The tools were quite easy to get up and running, a lot easier than the previous tool set. And the clocking is powerful. This particular part is a 28 nanometer part, so it's fairly modern in production and much, much faster than the older 65 nanometer parts. So way faster. It also has very powerful clock generation, phasing, locking, and timing capabilities. And so it was fairly straightforward to put together the logic that would do all of this. So a couple of questions come up. What are the alternatives for PPS marking? And I guess option 0 is you don't bother with PPS marking. Maybe you just assume all the samples are phase coherent and you don't need to know time. Another option is to invert the most significant bit of the samples for one cycle during the PPS event, which corresponds to a half-scale impulse. And on a receiver that's bandwidth limited, no actual signal should be able to do that. So it should be unique. But then the host computer's got to detect it and reverse it. And then once it knows where the pulse per second mark is, what does it do with that? We could also timestamp the signals, which may be a little challenging. And a third approach is to throw away the least significant bit of every sample, essentially making them 15-bit samples. The effective number of bits of the LTC 22.8 is less than 15, but the spec sheet doesn't say what it is. It does say that the signal to noise ratio, the noise is 78 dB below full scale. That's the noise floor. So if you plug that into the rearranged dynamic range equation, you'll compute that the effective number of bits is 12.66 bits. And most of the other wideband RF parts I could find that were 16 bits generally have a spec of about 12.6 bits. And so I think that 13 bits is really pretty much the maximum dynamic range of the part. If you do that, for example, getting rid of just the LSB, you free up 4 bits in the data stream to communicate pulse per second, and probably you can communicate a count of overload events in the last second. So there's 4 bits in every parallel sample word. of 64, where you could convey some information to the host. You'd have to go in there and look at that LSB and identify a particular state as the pulse per second, and then some other bits sequenced out over time as a count of the overloads. But the FPGA implementation that I have was it used about 6% of the logic and about 65% of the I/O pins on the device. So it's very much a I/O pin limited implementation. So in this case, if we run at 125 megahertz to the A to Ds, it's going to produce about 8 gigabits per second into the host computer. So the first question is there a host computer that's fast enough to ingest 8 gigabits per second on a continuous basis? It's a lot of data. Second question, KA9Q radio currently associates one receiver channel per USB interface, and this would present maybe 4 channels per USB interface. And so we might have to ask if KA9Q radio could deal with that. The third question would be, could KA9Q radio process 4 channels in parallel? You probably would want to maintain synchronism across all 4 channels while producing downsampled or demodulated outputs. And then you have to ask the question, what would KA9Q radio do to detect, and then what would it do with the information about pulse per second? You might try to put the pulse per second marks in the output demodulated streams, but because those are much, much slower, the time of a bit in a lower rate stream is much, much longer than the PPS mark of 8 nanoseconds that the FPGA puts in. And then we'd also have to ask what KA9Q radio might do with those overload marks. So if multi-channel is used for phase differencing, do we process all 4 channels as analog signals? Could we do something different? Could you time stage, that is time delay, the 4 channels and then sum them? In which case you might perform a beamforming operation before you convert it to an analog signal. Is there some other software that might deal with that? I think those are all meaningful questions if we're going to deal with high precision time stamping in multi-channels that we probably want to have a conversation about. So I've looked at ADC pricing. It's changed a lot in the last 3 or 4 months, both up and down. The LTC 2206 in 1,000 unit quantities is $62, which makes me wonder how in the world they can sell an RX 888 for 90-something dollars when just that one part is $62. The ADC 9648 we used on Tangerine is about $54, but that's 2 channels. It's 2 A to D converters, each of which is 14 bits. When we first did Tangerine SDR, that was about a $43 part. Here, about 5 months ago, it was a $350 part, and now it's a $54 part. So it seems like the 2206s appear to be available in China at a way, way lower cost than we can get them in the United States. And so if we're trying to compete on a cost base with a Chinese product, this might be a hopeless project. The Atrix 7 that Franco found, the 170 pin part, was about $32 last week. It's a very capable, very fast part. The FX10, we don't have pricing available. We don't even have a data sheet available. Franco posted a question to the Infineon website, and he got back an answer that looks like what we think the part does, which is 32 bits wide, double data rate on 160 megahertz clock. It also has a LVDS input mode, but I think there's only 16 bits available for that. And so that would require some different kind of processing. The requirements document we put together a couple of months ago looked at a base system cost of maybe $500, which is receiver and a GPS clock and a couple of other items, and an enhanced system, which had a much higher performance dual channel GPS clock and 4 channels. And we initially targeted that in the $1,000 price range. But looking at the price of chips we can get, it looks like we might be able to put together something that's a bit less expensive than those numbers. Again, all these component prices are changing dramatically in about the last 4 to 5 months. So that's some food for thought and what I put together over the last about the last week and a half.
Tom, I can obviously speak to a couple of those points when you're ready.
Okay.
When you just bring that slide back. When
Okay.
you're ready.
Yeah, let me get them back here.
Yeah, one thing, Tom, I'll mention that you're mistaking integrated noise for actual noise floor. If you look at the FFT of one of these parts in operation, if you look at the 2208 data sheet, the spot noise floor is down at minus 120 dB.
Yeah, but that's a result of integration over a long time period.
No, it is not. That is actually what its noise floor is. It's when you integrate it over the bandwidth that it comes up to where you're specifying it.
Okay. Well, the other ADCs, you know, their spec sheets list ENOBs of about 12.6.
Right.
I've never understood why ENOBs is different in the number of bits. I mean, can you point to some characteristic of the part that says why that's true?
Yeah, there's
I mean, are
noise
the
in the
steps
front end of the,
monotonic?
there's a noise in the front end of the chip.
Okay,
Yeah,
so
it's-
it's not
it's-
that it's an imperfect A to D, it's simply that it's got noise in the front end.
Right.
Some of
All
it's noise, some of it's nonlinearities.
Yeah,
Really a very complex topic.
Yeah, there's a bunch of factors.
But as
Alright.
I've mentioned, you know, I've worked with very high resolution A to Ds, and even though we specify them at like 110, 120 dB signal to noise, you look at them actually, look at the full spectrum, and these are 24-bit parts with a noise floor down at minus 140, and if you twiddle the lowest bit, you see it.
Because that's the
So-
part I don't understand. I mean, why are the bits included if they're not meaningful?
Yeah, the point I'm making is they are actually meaningful.
Okay, so that's what I don't understand. If they're meaningful, then why is the LNOB so low?
Yeah.
ENOB.
Yeah, on an HF band with a lot of complex signals, you know, there's a lot of question how many of those bits you can actually use due to
Well, that's the other thing.
intermod
Yeah, see,
distortion and other things.
right.
Well-
Right. They aren't really that useful as Rob is finding out now that he's gotten the SDR play to work just as well, even though the A to D converter is narrower. So
Yeah. So Phil, the question is, if you had a precision timestamp
all right.
on the high-speed samples, what would you do with it?
All right. Go to that slide and I'll speak to each of those
Okay.
points. All right. Okay. Currently, could it be restricted to associate 2 or 4 USB? If they come in together, yes. The big problem I would have if they came on different USB streams is synchronizing with each other.
Right.
I mean, I could do that, but if you give me hardware that gives me 32 or 64 bits at a time, and that hardware works, then sure, no problem. I would do independent FFTs on each one, but that's all. It's just not a problem.
Okay.
So yeah, I can certainly process 4 channels in parallel, given enough processing horsepower to do it. And I have a feeling, since I haven't even looked at using GPUs yet to do the FFTs, that this would not be a problem. As it is, most medium high-end machines, I still have plenty of idle time, cores actually, to do this. Now, the caveat there is I might start running into memory bandwidth problems. Just because the cores are idle doesn't mean I can actually use them, right?
Right.
Might discover that if I start running another core, then the previous ones are going to slow down drastically because of memory contention. So a lot also depends on things like cache sizes. So
Right.
that's caveat. Okay. Could it maintain synchronous across all 4? Yeah, sure. If they come in together on a single USB stream, yeah, I don't see any reason on that. Okay, how would I detect the PPS marks? What would I do with them? Well, I mean, you tell me. If you're going to start playing around with low order bits, I can just look for those. It would cost me a few cycles to do that, but I'm already looking for overloads and counting overloads, stuff like that.
Okay.
Okay, what would I do with overload marks? Well, I mean, what I'm doing now, I'm just keeping counts.
Okay.
Okay, so let's see. Did you have a previous page that you also? Okay. Wait a minute. Oh wait, wait a minute. There one or two slides here that dealt with KNICU radio. Let's see.
I think it was all on one slide.
Okay, all right. Okay, so what would I
yeah.
do with? Okay, all right. What I would probably do is I would synchronize the 1 PPS with the beginning of a frame. You know, internally, KNICU radio does FFTs of blocks of a fixed size, with typically 20 milliseconds, but you know, it could be changed. So 20 milliseconds has been a handy size. I would simply align the 1 PPS to be at the beginning of a 20 millisecond block every 50 blocks, right? Which will be 1 PPS. That is slow enough that I could give you out of band information, or I could simply internally, I keep a modulo counters. I count blocks, you know, in a modulo fashion. Maybe right now, I do it mainly just so I can keep track if I lose any because of scheduling problems. But I could easily synchronize that counter with you know, the repetition of the 1 PPS. So internally, I can easily say, okay, this block begins on a second boundary. Okay, now there's some overlapping, but you know, I can do the bookkeeping required to keep track of that. Once it goes to the FFT, once it goes to the filter, there's going to be, of course, some latency in that. Obviously, these filters are causal, right? But then the question is, what are you going to do with it? Okay, I can now deliver blocks that are at some absolute time. Now, what are you going to do with it? I mean, right now I just spit them out as Ethernet frames, and I could say, okay, this Ethernet frame started on this sample, and if you know the group delay of your filter, then you know you can apply that and put an absolute time on the block that comes out. I could, if you want, synchronize the RTP timestamp to that. I mean, it's actually not that hard to do any of these things, assuming that, first of all, I've got enough hardware resources to do all the excess processing. And the most important thing is that the USB delivers the samples together, and I don't have to try to somehow figure out how to synchronize independent USB streams. That would be a real pain in the butt for me, since I don't really understand the internals of USB.
Yeah, I think you can think of the applications, for example, if you know that all the frames are time aligned, then you could put them through different time delays and essentially build a beam-formed antenna. Or you
Okay, if you're going to do a beam forwarding, you got to do that at the full sample rate, right? At the RF side filter.
Yeah, everything has to be matched up at the ADD sample rate.
Okay, so what kind of processing would it be involved? I haven't actually looked at beamforming. What would it just be, a general purpose matrix multiply of some kind?
Well, you know, if you have yeah, it might be. I'm not sure. I haven't looked at if it's just if you have two time aligned channels, if you can just sum and difference them.
Okay, yeah. Now, how many of those are you going to want? How many beams are you going to want to form at the same time? Because you've got two inputs, right? I could give you the sum or the difference, right? If you had more than two, well, right now, you know, thinking ahead, if you had more than two, you're going to want probably all possible combinations. Things start to get out of control here a little combinatorially, but I don't see this as being a showstopper, especially if I start using GPUs. The important thing, as we keep discovering, is the hardest part is not processing the data, it's moving it around. Every time I say that to a group, I look out and I see heads nodding. So this is not the only one to discover this.
Yeah, that's that was the bane of the previous project.
Right. And it's a little surprising too, you know, because you know, those who have been around for a while, we know that the FFT is like the gold standard benchmark for this sort of thing, and they used to run really slowly, and it's hard to believe that they're now so fast. And they're so fast that they disappear under the cost of moving the bits in and out.
Mhm.
but that's the new reality. And not a bad reality to have. You just got to keep it in mind when doing system design. That's all.
Yeah. Okay, so it sounds like this kind of an approach could be useful and doesn't, at least from your point of view, have any software showstoppers.
No, I don't see any showstoppers, assuming that the hardware is fast enough to support me. I don't see anything wrong.
Yeah,
I don't see any reason I can't extend the architecture. But the main thing, again, is give me the samples synchronized in time, and don't expect me to put them together from independent sources. That would be a
right.
nightmare. So,
Yeah, yeah. So if we go back, that's kind of the idea behind the concept here.
Well,
yeah.
Phil, the thing is that at some point, we would like to be able to bring in samples from widely separated receivers and have them time
Yeah.
synchronized.
Well, that would probably be after they've been downsampled, right?
It could be anything.
Could be anything.
I mean, you could downsample it or not. The
Yeah.
question is, how do you bring it in?
Well, if
and
you
one
don't
thing,
downsample, and again, you're moving around a huge amount of data. So
yeah, and Tom's asking, is there other software? And well, there's lots of other software to do multi-channel processing. One example that's out there that I'll point out is the SuperDarn system, which has been doing beamforming all along, but it's been a slow scan form of beamforming. And they've just upgraded some of them to simultaneous beams, so that instead of scanning across the from, in their case, left to right, they're pulling them in
parallel
all
rather than
at
serial
once.
beamforming. I got
Right.
it. Yeah. Which is just n times the amount of work. Okay, I got it.
But the hardware is there to do it. I know they've got a lot more, but that doesn't mean that ours couldn't do that with a number of units parallel.
Yeah. In terms of robbing low order bits, I don't know, for some reason it just seems unclean to me, but I don't see a better alternative. It's very reminiscent to rob bit signaling.
I do sort of like
PCI
the idea of
systems.
doing a phase reversal that just would not happen in real life, and then you just say, "Oh, there it is," and you flip it back.
Are we sure it couldn't happen in real life?
Well, here's the other thing: it's happening every second, exactly
Yeah.
a second apart. So said number of samples. So it's really just a matter of synchronizing.
Remember,
If you have a little bit of noise
minimize,
in your
I want to
synchronizing,
minimize what I do in every sample. They're coming in fast. So, I mean, even checking for overloads and counting overloads takes a noticeable amount of CPU. Not
right?
extreme, it's just noticeable.
The one thing I want to say is that everything here happens in the FPGA, so it's in software. So as long as we have all the signals, we can decide later on, Dave and Phil, a different scheme to encode the information. It can be implemented in the FPGA, in a bit, and we just push a new bit stream. Makes sense?
So we're going back to FPGAs. All right.
Yeah, this one is simple. I was able to write the Verilog code for it in about a day.
Yeah.
And
I'm just thinking about future problems with supply chains and, all the problems we've had to go through in the last few years with these things.
Yeah, this is a much more current and capable part than the previous one we looked at.
Yeah.
And
So the main reason for using the FPGA here is to synchronize and make sure all the ADC signals are phase coherent, and then to make sure that, and then to do that, the multiplexing.
Yeah,
right.
It's primarily a big multiplexer that's
Yeah,
sufficiently
I can
fast
see
to
that,
get it
yeah.
all into the FX10.
Yeah, the
you
logic
still
for that is real simple.
What prompted me to really think about what I was doing KNIQ radio was during the chip shortage, when you guys at TAPR, I mean, you actually got a big grant from us at ARDC just to build an emulation kit because you couldn't get the FPGAs you needed.
Exactly.
Yeah. So, I mean, that was one of the things I was thinking about, and I'm wondering, why do we need these things in the first place? So you guys, in my mind, make a good case for an FPGA to use one these days.
Yeah, well, the original reason for the FPGA was to actually do downsampling.
Right, because the computers weren't fast enough. Now they are.
Yeah. Right, so on Tangerine, the FPGA was to turn it into Ethernet frames and send it out as Ethernet frames. But
Yeah,
that
Ethernet still
required the
not fast enough.
FPGA to implement a complete TCP IP stack. And a lot of problems cropped up there.
Yeah. Instead of using USB, why do we why not go to 10 gig Ethernet?
Well, one of the key things is that we have this FX10, we're assuming part, we have an FX3. It's a fairly low cost part that's capable of running USB at 10 gig from a very simple logical input.
Okay. All right.
So that's an advantage. And the RX 888 is using the FX3 part.
And
I think
the
there are
other
other front
reason
ends. Aren't there other high-end front ends that do use 10 gig Ethernet or faster?
Yes.
I mean, for
they
one
do.
thing, is that 10 gig E comes with fiber almost for free.
Right.
yeah.
Right.
And
that's the
I
advantage.
really, 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 really like the idea of fiber between this and my computer.
Right.
But the other reason, Phil, is that
Well-
all those billings computer then cost nothing. They all come with USB 3.2 at 10 gigs, so you don't have to buy anything else to
Well-
connect to
Oh,
the
I know,
FX10.
I know,
Yeah.
I know.
Well, Tangerine was moving in that direction. We may be able to make use of some of the development that's been done. It had 1 gig in it, and the next iteration was going to
Yeah.
have 10.
Yeah, the current design, I calculated the maximum possible throughput of Tangerine is about 200 megabits per second.
Yeah, but I would really, I mean, I'd be willing to pay real money to replace all my cables with fiber these days if I could get the hardware that, goes on the ends.
Right.
Yeah. Well,
So
as I'm
hook
trying
this
to
up to
point
your
out,
host and then put a 10 gig on the host.
we've already done some development in that direction.
Well, 10 gig fiber, 10 gig cards are not terribly expensive right now. But the other alternative is to use perhaps the next step up or two in the same family of FPGAs to allow you to use PCIe output from this and go straight to a USB 4 type interface to get it out of your device and into another one. There is another project out there that has recently, I don't think they have quite the same objectives or constraints that we have, but the group, what do they call themselves? Wavelet Labs has these mu SDRs or mu SDR and SDR. Anyway, I have one of these things, which is a little M.2 card that plugs into an external M.2 interface. It doesn't buy you a lot of distance, but it buys you a meter or so away from your CPU at very, very high speeds. And their new product that they probably will talk about at Canoe. They talked about the last one at Canoe Radio meeting last year. They'll probably be at the Canoe Radio meeting this year talking about this newer design they have that uses 4 of those. Now, what they're doing is they're putting 4 7000 series Mirix chips. The older one had a 6000 series Mirix chip and an Arctic 7 or whatever the same family of FPGA as we have here, except that one that has 35 LUTs, 35,000.
But all this is copper. I mean, why do they keep using copper? Why can't we
Well-
kill copper?
Well,
Yeah.
it's just how, it's hard, it's awful when you trip over fiber, that's all.
Yeah. One thing to keep track of here, one of the big problems in Tangerine was the implementation was phenomenally complicated. There was a huge pile of Verilog, a huge pile of C code, that ran in the processor on the FPGA. It had a lot of things in it that required licenses to put in the FPGA. This particular concept here has no licensed IP property. So all the tools are completely open source and are free because it's really not doing anything very complicated. The FX10 has a lot of that complication. I'll leave that to Franco since he's programmed the FX3. I think a lot of that is available. And so from that point of view, I think the design is much simpler.
I'm all in favor of this if we can get the FX10s.
Yeah.
But if for any, and I think this is the way to go, but if for any reason we could not get the FX10, for instance, we could go to the, I think we're looking at the, what is it? Something 7, 10. I can't remember Xilinx's numbers, but it's the 10T or something. And the next one up more or less is the 35T, and it's not much more expensive. They didn't sell a developer board at that Chinese place that we were looking at. They sold 100, which is for not much more. And but it does come with CERDES hardware that does not require license. My understanding is it doesn't require licensing to use. And this is a difference between Lattice and Xilinx and some of the others. They license that CERDES stuff. As long as we're not trying to do TCP/IP in the FPGA, we're pretty good. But if we try to put fast, even not so fast TCP in the FPGA, we're going to start talking about buckets of money.
Who say anything about TCP?
Well, you were talking about 10 gig Ethernet, I suppose.
Maybe not Ethernet. That doesn't mean TCP.
Yeah, I guess you're right. I get it. Okay, yeah, you're right. And I don't know what that would imply.
It
I
implies
haven't thought that
putting a
far.
fixed header on the front end and shipping out over the Ethernet hardware.
That's a thought. Now, because you've already, I don't know. Never seen anybody do that.
Yeah, maybe we just need to get a USB to fiber adapter.
But didn't John Ackerman find such a thing?
I don't know. You'd think it might be available.
I think he did. I haven't talked in a while, but I think he had problems with it though, because it only operate in like super speed mode, and would not have a backward compatibility mode. But anyway, that was a few months ago. I didn't track what he was doing.
You can buy USB to fiber adapters, yes.
Excellent. And will they operate in both modes?
I don't know how fast they are or what mode.
Because man, that would solve so many problems. Although I know USB doesn't have some round trip time limits that would limit the length of any fiber or any cable. Yeah.
You're talking about a raw stream over USB, but converting it to Ethernet and then receiving it, converting it back to something from.
Well, it's not Ethernet so much as it is fiber and a simple, easy to use interface.
Yeah.
That's both of those would be important to me.
I get it.
Ideally, what you'd like is a USB cable that's about 50 meters long, made of fiber that, looks like a USB copper cable.
Exactly. I dream of putting this up on my roof, running fiber into the stack. Oh man, I would love that.
Yeah. Okay. So, Bob, thank you. I had to relearn Verilog last weekend.
Good.
Thank you for the book. So anyway, that's what we've been up to in the last week. And it sounds like if we sit on our hands and wait for an FX10, maybe the concept is usable.
But yeah, I answer your questions about my stuff. I don't see any showstoppers in the architecture doing what you want, as long as the hardware's fast enough for me.
So,
okay.
Tom, can you work out or at least demonstrate this with two ADCs and your FPGA into a slower FX3?
I don't know. I've got a data sheet and I don't think the FX3, I have to go look at what the hardware interface on the FX3 looks like. I've never gotten one to play with it. The 10, at least we know from the product brief, has 32 CMOS lines that are DDR. That's about all we know. I'd have to go look at the 3. Obviously 16 bits CMOS is what goes into the FX3 because it takes one ADC in, and I don't know that the FX3 could do two ADCs. I don't know if the hardware would support it.
The
Wasn't
only
somebody
reason I'm
working
asking,
on that design?
sorry.
Who was it who
Double.
was working on that design?
What? Not with
The
two,
ADCs into an FX3.
not with two.
So,
I know I
Phil
was helping
Harmon.
somebody. I can't remember who it was.
well,
Phil
are you
Harmon
thinking of
and
what Phil
Gene-
Harmon's doing?
Yeah.
Uh,
I don't know that we've heard from him in a while.
yeah.
Right.
And
Well, we might check.
Franco's really the only one to know anything about it.
Yeah, so the idea here was to try to make the software on the FX10 look as close to what's on the FX3 as possible, just to minimize the risk and the development effort in the concept.
Yeah. Well, what I was thinking about is ways to work on this without having to have an FX10, because that seems to be the bottleneck.
Oh, yeah, it is.
I mean, do we really need to use a protocol across this the channel? I mean, this is basically a spigot of samples. I mean,
Yeah.
even the USB involves various kinds of protocols set up and so on. Could one just take a media converter, fiber, copper to fiber media converter, and just feed it a series of bits or bytes and create a card on the receive end that just took those bits or bytes and shoved them into memory? And, because this isn't the end. I mean, if we the sky's the limit in terms of how many samples you want to shove down this. And I agree with Phil, getting rid of the copper is extremely valuable. I don't think we haven't even started to look, but at the impairments RFI introduced by the use of the USB cable with the ARX 888. The few places I've looked, I've seen a lot of garbage that's being introduced by the connection to the host computer, and this is the biggest problem with receive sites is how do you get rid of the ground loops so you can actually hear the RF, and separating the receiver electrically.
Amen. Tell it, brother.
And that's what, and that's why we needed the K9Q web to be able to start to see how bad things are at sites when you have a copper connection from the A to D to a host computer. So
Testify. Say hallelujah.
and so I would wonder whether our application, I don't know if there are others that have, this may be kind of a unique data transmission application where you want to transmit data without introducing ground loops. So it might warrant an investment in I hate to say it, proprietary, fiber-based data transfer mechanism that would involve a PCIe card on the receive side with a fiber on it, and maybe these, and something attached to Tom's FPGA that would just take the FPGA output and convert it into pulses of light.
Let me mention that Dell has a card that is a PCIe with a fiber interface on it. It'll do 8 gigabits per second.
What are I don't know PCIe very well. I mean, I went to very, very, very rudimentary level. What are the delay restrictions on that? How long could the fiber be just for delay?
Electrically, I've
No,
seen,
time, electrically or optically, it's timing either way, speed of light.
It's
Effectively, USB 4 is kind of PCIe or with some wrapping, protocol wrapping.
Okay, well, I don't know PCIe though. What are
Yeah,
the
I'm saying, but I'm saying the specs for USB 4, the generally acknowledged ones are, you know, a meter or a little meter and a half for copper with good quality cabling that is well, it's kind of thick and a little stiff. It's like the Thunderbolt ones, but this is one, for instance.
but does
Hey,
it
but is that
but does it-
electrical? Is that an electrical limit or a
that's a
timing?
that's a
I I think it's, I don't know. That's that's a consumer oriented limit. I mean,
One's fundamental, the one isn't, right? In
yeah, it's
terms
not
of
fundamental. It's more about, you know, getting adequate signal across there for all consumer applications.
but that's a copper cable, right? That's not a fiber
Correct.
cable. Okay, so that
Right.
means that you have to at some point communicate the ground has to be shared between the remote device and the host computer. And so we haven't avoided the ground loop problem. We've just increased the speed of the
Oh, you don't
of the channel.
necessarily have to have common ground. You can have isolation transformers. So why not just avoid the whole problem and go optical?
I agree. I'm all
So
for
many problems just disappear.
yeah.
Does a link between the radio and the computer need to be duplex, or can it be a simplex link with just data
It's
coming out of it?
it's yeah, I mean you know you need to have some way to configure the receiver, but you could as hard, you know, it's hardly that's a one-time operation generally.
Yeah.
So you could have a you could have a setup mode where you plug in or connect to a little web page on a via Bluetooth or Wi-Fi. But after that, I would think you could just connect up a fiber between this, and there's this unidirectional spit of data is just coming down the fiber line, and the host has to understand the format.
Well,
Of course,
if you're doing simplex, then the length of the fiber isn't going to matter anymore.
that's right. Then it doesn't make any difference. Yeah, you can remotely.
Well, that's why I say Ethernet, because Ethernet is a half duplex. Well, I mean, it actually can handle full duplex, but it does not require it. You know, you can just transmit continuously in one direction, and there's no length limit other than the attenuation limit.
I think Ethernet's a lot more attractive than fooling with USB stuff type equipment because Ethernet is well established, and the hardware has many applications, many media, many interested parties. The USB is really complex and only getting more so.
Right.
Thunderbolt was simpler in that it didn't try to be everything for everybody, but it's really the same thing.
Well, yeah, I mean, stamping a header on a UDP packet and shoving it out, that seems, that seems like maybe the FPGA could do that much work. I mean, you don't need to move anything in memory. I mean, if you have scatter gather DMA on the that you create on the FPGA, the samples could come in, the FPGA controller could code could create a UDP packet by linking a header plus the data payload and just ship it out.
How hard is it to implement scatter gather DMA on.
I don't know. I did it in a computer back in 1986 with a
That's
Seek
an old
chip.
idea.
It's an old idea. I was able to get wire speed disk I/O across the at that time 10 base Ethernet, but the
Yeah.
disks weren't any faster. So
Just
I
a
was
floppy
basically
disk.
I got disk speed across the across the 10 base T network. But the same idea should apply. I mean, Tom would know better what the resources
Yes.
are inside the FPGA, but it ought to be. I would think it would be something that would be pretty straightforward to implement. And
Yeah,
FPGA code.
there is PCIe things available in the FPGA. They are licensed. You do have to buy them. And you need a license to
I wouldn't be talking about US. I mean, would you need the PCIe to talk to a fiber Ethernet chip? That's the idea. Can you talk?
Okay, what?
Can you talk to a
Go ahead.
fiber Ethernet chip and tell it, here's the whole stream, just send this out?
Probably not.
Yeah,
The optical modules like an SFP plus
yeah,
is just basically 1 bit wide. It's an analog.
yeah.
It basically produces a single 10 gigabit per second analog stream. And
Yeah.
then the far end recovers clock. It produces a 10 gig stream with
Yeah.
no knowledge of what the bits mean.
Yeah, well,
And they're very
Yeah.
common.
Yeah, they're very inexpensive. They're in the,
Oh, yeah.
I've seen them in the $20 price range.
Well, this
It's
card
simple.
that I posted the link to is $100. It does fiber from Dell, and I don't know if they publish their protocol or not, but if they do, then there's.
Yeah, there are no, I've been looking for standalone PCIe chips and, there's a name for them, PCIe target or client chips. I have not been able to find any, standalone chips. I've only been able to find the intellectual property for the modules on the FPGAs. And I've not looked further into what it takes and the signaling required.
Yeah.
Can somebody tell me? Can somebody tell me how PCIe works at a very, very basic level? I mean, my knowledge is that it's a bunch of parallel differential lanes that each run at some speed. You can stripe data across them. That's really the limit of my knowledge. And there's a whole
Yeah.
bunch of different speeds because of different revisions. But what kind of timing and control has to run end to end that would limit the latency, limit the length of a cable, if electrical limitations were not a problem?
One of the problems I found was I couldn't get the spec. You have to buy the spec.
Huh. Well, that tells you right there. There's a
Yeah, but essentially they're bit serial and the parallel lanes at the receiver have to be de-skewed and aligned to get the data transfer, but it's intended to be a bunch of individual serial links that are running up in the, 2, 4, 8, 16, 32 gigabit per second per pair
Right.
line rate.
Yeah, that much I know, but is there some higher level control, a handshake that requires one end to ask for data from the other end each time? Like I think you'd have to do a USB.
I
You see what
believe,
I'm getting at? I'm trying to get at what is the latency limit here if
Yeah,
electrical is not a problem
yeah, I believe there is handshaking required.
on each transfer.
Yes, but the transfers can be fairly large.
Well, those data rates, that's still not very long in the wire, is it? I mean,
Right.
Yeah.
Yeah, so anyway, I spent a while trying to research that during Tangerine, but I kept running into document paywalls.
I have a few thousand pages of documentation you could have.
That in itself is its own form of paywall. It's measured in hours instead of dollars.
I have a whole book from I think Intel that they published about it at one time.
Okay.
But on the other hand, there is a set of videos about Linux PCIe by a German guy. I've only watched a few of them. I'm always mean to go back and watch it. They're very thorough and they're They cover the whole thing, but I think there's 10 or more of them. I can't tell you the name right this instant, but if you're ever interested, I'll be happy to give them to you.
Yeah, the one concern I have is if we start getting into the details of the computer hardware interface of the development effort exploding unknowingly.
Right. That's
I-
why I like Ethernet.
I agree. It gets to be a monster. And so so an established protocol that's supported by a variety of kinds of silicon is a protocol or protocols. All this stuff has layer upon layer of protocol, depending on what you want to do. But you know, there's a complete kernel driver in Linux to handle all of the, or maybe multiples. And there's and in Windows and everything else. It's a pretty important area of development, but it's also technical enough. It doesn't get discussed in details in the, you know, in a lot of the magazines much. But the information's out there, but a lot of it's painful,
Yeah.
Page after page after page of timing diagrams and stuff. And I haven't got the mind for it, but
You're talking PCIe.
yes.
Yeah, well, I mean, the one argument for PCIe is that it's potentially faster than any of the Ethernets. I think how fast does Ethernet go now? 100 gigabits? Is that the fastest?
Oh heavens, there's 800 gig Ethernet. I worked on 400.
Okay, so it
Before I
does exist.
retired.
Obviously, it's going to be rare. 10 gig is not that hard to get now. Are we going to need anything faster than that?
Yeah, the difficulty, can you find chips that essentially translate a raw data stream into Ethernet compatible framing that's simple to use and inexpensive?
Well, that to me would be one perfectly valid use of an FPGA.
Yeah, there's a lot to Ethernet framing.
Not really.
Yeah, I
It's
worked
changed
on
since
it for
1980, really.
Oh yeah, it's changed a lot. When
How?
you get up to 10 gig, you have all kinds of multi-block framing and alignment and identification, swapping.
Oh,
The spec for the 10 gig processing is several hundred pages long.
oh yeah, they're scrambling and they're okay. All right, never mind.
There's
right.
a lane
I'm thinking
alignment and
one
there's
level up.
slipping and there's lane coding. There's a
Yeah.
bunch of stuff that goes on.
Yeah, one level up though. I mean, the Ethernet frame hasn't changed since 1980.
Well, that's true, but when you get above when you get into fives with multi-lanes, all kinds of complicated stuff starts happening.
Yeah.
I was looking at some timing stuff on the PCIe, and it looks like it might be limited to 8 gigabits per second. That's maybe a limitation on transferring the data.
It limited to what, Bob?
The PCIe interface. It comes back to the same kind of spec that Dell has on their card.
Well, it
What was
depends
that
on
limit?
how
Was
many
it a
layers.
That's a per lane limit. Each lane
Per lane
has a
limit,
piece. Yeah, there's 16 lanes, up to 16 lanes.
32 sometimes.
Yeah, I guess.
Well, I
Yeah,
was seeing numbers like 2 gigabits per second per lane.
Yeah. That's
is
the
not
original
really the
PCI
problem.
spec.
I don't see speed as much of the problem as the end-to-end latency limit on handshaking.
But that wouldn't be a limit if you're running simplex, I think.
Well, no, but the question that I keep asking is whether PCIe actually does run simplex at the lowest level, and it sounds like it doesn't.
No, I don't think so.
I don't think so either. Yeah.
Yeah, so that would set, I mean, that would be a limitation how far you could extend this over fiber.
Yeah.
Because the speed of light is still the speed of light.
Yeah.
Even if I could
say looking into this Dell card for $200, you could get 2 of them and just talk computer to computer and see what you could do and how hard it is to work with.
So one thing I learned in the Windows world is you want to stay out of kernel programming.
Yeah.
Guys, I would like to, if you don't mind, You were mentioning there was a discussion about PPS detection, and I was wondering if anyone has settled on, or at least an idea of how PPS detection was going to work, whether it was going to be something in the CPLD or FPGA, or the FX10, whatever that would eventually be, or if it would be something done in software, because I had mentioned a method a while ago, which I think has quite a lot of merit, because it already has an example of GPS timestamping data from an RTL SDR, and the concept is actually fairly simple. So what it involves is you start with some carrier frequency. Let's call that the timing frequency, and then it's gated on and off through a FET, and what gates that FET is the pulse per second from the GPS. In the example that I was talking about, that frequency was generated by the time pulse 2 output of an MAT, a U-Blox MAT, and the pulse per second was what gated the FET. And this was the so the software looked for these pulses in the IQ data at this frequency, or a harmonic of that frequency. And I wanted to show a screenshot of what was currently, it's loading, but this was a method that actually works really well. So it was developed by Paul, the author of VLFRX Tools, and I think this method has some good merit. The timing or the software that looks at the IQ data.
Your image hadn't come up yet there, Jonathan.
I apologize for that. Yeah, it's loading. Let me see. I will post the link. Well, my Zoom just froze up.
We still hear you talking. Maybe.
Whoops, I apologize for that. Let me try that one more time.
We see it now.
There we go. So this is the application of detecting VHF meteor scatter using a VHF carrier. And it would detect pings from reflections caused by meteors, and it uses an RTL SDR. And this is an example of the circuit, the very, very simple circuit of feeding in a reference signal and gating it with the FET using a pulse per second. So I felt that this would this method here has some merit, and um, um, what do you guys think? Is it something that's am I thinking all wrong? But it looks like that it's definitely pretty useful, and we could utilize the source code um, from VT Time and VLFRX tools as a guide. So that's kind of what I wanted to share with in terms of pulse per second detection, which I think is going to be important and very useful because it already is in VLF. I'll post the link in the chat if anyone wants to do some further reading. Oops. And yeah, that's all that's all I wanted to mention was this method, which was already tested and working.
Yeah, I think the UK astronomy group is using that for their meteor detection and time embedding. And we're just developing it recently, I believe.
So I joined in late in the discussion, but what were the pulse per second detection methods that were talked about?
So Tom showed a signal coming from a 1 pulse per second feeding into the FPGA for a synchronization in this block diagram.
Yeah, it's, anything's possible. An option is to timestamp individual samples. An option is to do nothing with it and do it analog somewhere else. There's a couple of options. I think right now having some flexibility is probably good.
So what this method does is, so it feeds in this gated reference signal, and then the software finds the pulse per second and realigns the sample according to UT time. So like, as Phil was mentioning about sample realignment, that's what this software does, is it realigns the sample to UT time based on the detected pulse per second. And it's done all in software. So I believe that this is that doing it in software is totally possible, or at least this would be this would be something that would be useful for hardware such as the RX 888. If you don't have a reference feeding it, or it might even improve the timing performance. So that I felt that this would be a really good idea. No one has any?
Yeah, I don't know what kind of accuracy the approach can achieve? Do you have any, have you have measured how precisely the timestamps are aligned to PPS?
No, this is no, there hasn't been any. I personally haven't. But
Yeah, so you know there's probably different applications of how precise does PPS need to be. You know, if you're interrupting a 7 megahertz carrier, you know, I think you'd have an accuracy on the order of 1 cycle of a 7 megahertz carrier. But I was just wondering if there have been any measurements of the software that uses the approaches show.
well, the software does output timing measurements with each detected second. That was in the that was on the page. Yeah, I posted that in the chat. It might be it might be worth further reading, but this method works for VLF. It works with sound cards. It's accurate enough that a lightning location network it has been realized and built and is functional based on this method of feeding in a pulse per second through your data acquisition, which is why that I feel that this method has merit. If it didn't work, then then a lightning location network would never have been possible.
Well, one thing about Tom's proposal there, he suggested 2 or 3 ways to get the data into the stream and recover it. So he's got an accurate way to do it now without having to do the modulation or do the special signal modulation and then decode it in software. Although there is going to be some software decoding required on the part of Phil, I guess, to separate it out.
Well, I'm not talking about what would be. I was only talking about for the RX 888.
Okay.
So this method that I described, this was this is something that I'm suggesting for the RX 888.
Yeah. I mean, there are devices like the Kraken SDR, which use similar software